Hey, I'm Lewis, and I'm going to teach you about a new kind of differentiation today.
Whoa, whoa, whoa. Hold the phone there, buddy. I've been teaching calculus for 14 years now. I think I know differentiation a little bit better than you do.
Okay, chum, let's see what you've got. Show me how it's done.
Lucky for you, sweet Lou. I have my lesson plan for my students all made up. Let me grab it for you. Right here. The easiest way to differentiate y equals x. Explicit differentiation.
Explicit differentiation? Isn't that what we've been doing this whole time?
What do you mean? Isn't this the easiest way to differentiate y equals x using the power rule?
Well, yes, if you're dealing with simple equations like x equals y. But Zach, what about a more complicated equation? Like, let's say x squared plus y squared equals 1.
Please, well, it's just a circle. Here, I've got a graph right here. If you look, I've already solved this problem. Not that much work there, right?
The issue with this work is that this equation isn't a function.
What does that have to do with anything? Who gives a hoot? Are you really trying to tell me that I've been teaching my calculus classes incorrectly for the past 14 years? Fat chance.
Well, explicit differentiation isn't wrong. There's just an easier way. Here, we'll break it down. What are we trying to find when we solve for the derivative?
Come on, Lewis. Even my Algebra G students know that we're trying to find the rate of change at a certain point.
So let's find the derivative of x squared plus y squared equals 1 in terms of x without solving for y. Since the terms are being added, we can use the power rule. X squared derives to 2x to the first, and y squared derives to 2y to the first. And the derivative of 1 is 0. There's one more step though. Because we're deriving in terms of x, we need to multiply the derivative of y by dy over dx. This represents the change of y in terms of x. The next step is to simplify this equation by solving for dy over dx. Do you think you follow this?
Yeah, I think I got this. Let me take this over for a minute. Let me just simplify this real quickly. So we got 2x equals negative 2y dy by dx. Then we will solve for dy by dx so that it equals negative x over y.
Great.
Does that look good?
Yeah, that does. Here, let's check our work now. I have a graph of x squared plus y squared equals 1. If we take a point, let's say root 2 over 2, comma, root 2 over 2, and plot it.
Right about there, would you say, Lewis?
Yeah, that looks
okay.
right.
We'll say that's
Trying to find the rate of change is a bit difficult. But if we take our point and plug it into the equation for dy over dx that we found using implicit differentiation, dy over dx is equal to negative root 2 all over root 2 over 2. Or dy dx equals negative 1. Does that look accurate?
Yeah, it does. The work's right here. It shows it.
Okay, Zach, let's see if you can handle a harder one.
I think I can do that one, Lewis.
Try this.
All right, Lewis, I think I've got this one for certain. So what I'm going to do on the left side of the equation here of x cubed plus y cubed is use the power rule to simplify that to 3x squared plus 3y squared times dy by dx. And then I'm going to set that equal to the left side using the product rule this time, so that it is equal to 4y plus 4x times dy by dx. Now, since this problem is asking for me to find the tangent line at that certain point, which is 2, 2, I don't need to go any further, really. Now what I'm going to do is I'm going to plug in 2 and 2 for x and y, and I'm going to find it out that dy by dx is equal to negative 1 equals dy by dx. So from here I need to put that equation into point slope form. So we will have it equal to y equals negative x minus 2 in parentheses plus 2. And there's my final answer, Lewis.
Nice job, pal. You're a really fast learner.
I know, it only took me 14 years. I'm definitely going to bring this trick back to my calculus. You're the best ever, Lewis.
Oh, thanks, Zach. Okay.
Let's